Welcome to the Deep Dive, where we cut through the noise and deliver the most important insights from the cutting edge of AI research directly to you. Today, we're diving headfirst into an incredibly exciting new frontier: Agentic Intelligence. Forget simply responding to a prompt. We're talking about AI models that can perceive their environment, plan multi-step actions, reason through complex scenarios, and then act autonomously within those dynamic settings. It's a profound shift, and well, it's happening now. Our mission today is a deep dive into the Kimi K2 technical report. This isn't just another language model, it's a significant leap towards truly intelligent agents. If you're an AI researcher or an ML engineer, understanding models with these agentic capabilities is absolutely crucial for staying ahead. And this deep dive offers you a vital shortcut to what makes Kimi K2 stand out. For those of you who want the key takeaways up front, here's your 1-minute summary. Kimi K2 is a massive 1 trillion parameter mixture of experts model. But here's the clever part. Only 32 billion of those parameters are active at any given time, making it incredibly efficient.
What's truly groundbreaking is their new MuonClip optimizer, a brilliant piece of engineering that allowed them to pre-train on a mind-boggling 15.5 trillion tokens, without any of the usual crashes or loss spikes you see with models this size.
Yeah, that stability piece is huge.
Absolutely. And the post-training is where Kimi K2 really shines in agentic capabilities. They developed a revolutionary multi-stage process, including large-scale synthetic data generation, essentially, teaching the AI by simulating thousands of tasks. That's then combined with a reinforcement learning stage, where the model learns by doing in real and virtual environments.
Which is key for that agentic behavior.
Exactly. The payoff. Kimi K2 is setting new, state-of-the-art benchmarks among open-source models, particularly in agentic tasks like software engineering. It's showing remarkable strength across the board in coding, mathematics, and general reasoning. This positions Kimi K2 as one of the most capable open-source large language models released to date. And critically, they've made the base and post-train model checkpoints openly available to the community. So let's unpack this further. The report talks about a profound paradigm shift towards agentic intelligence. When you hear that, what's the core idea that should really resonate with our listeners about how we're building and interacting with AI now?
Right. What's truly exciting about this paradigm shift is moving beyond what we've traditionally done with AI, which is, simply training models to imitate human-generated data.
Just copying patterns.
Exactly. Imagine an AI that doesn't just respond, but thinks for itself, actively perceiving its environment, formulating multi-step plans, reasoning through complex scenarios, and then executing those actions autonomously. The belief here, and it's a powerful one, is that by enabling an AI to explore and exploit its own experiences, it can acquire capabilities that go beyond what human-generated data alone can teach it.
So potentially leading to truly superhuman performance.
That's the hypothesis, yeah.
Potentially. However, this isn't a simple jump. The report really highlights two major hurdles.
Right.
First, in pre-training, how do you efficiently instill broad, general-purpose knowledge when high-quality human data is limited? This is where what they call token efficiency becomes absolutely critical.
Getting more bang for your buck from the data. Precisely. And then in post-training, how do you translate all that foundational knowledge into actionable, intelligent behaviors, especially when tasks requiring multi-step reasoning, long-term planning, and advanced tool use are notoriously rare in natural data sets and, frankly, incredibly costly to scale?
It sounds like a monumental engineering challenge, and Kimi K2's team seems to have tackled it head-on. Let's start with their foundation, the pre-training. This is an enormous model. What were the core architectural decisions that set Kimi K2 up for success in pursuing agentic intelligence?
Indeed, the architecture is fascinating. Kimi K2 is a trillion parameter mixture of experts, or MOE, transformer model.
Right.
But as you mentioned, only 32 billion parameters are activated or used per forward pass. They derive this architecture from extensive empirical scaling law analysis, basically testing what works best at scale, which led them to push the number of experts to 384, quite a jump from 256 in models like a DeepSeek v3.
Okay, and why more experts if fewer are active?
Good question. What's important here is that their research revealed increasing sparsity, meaning fewer experts active at one time, consistently lowers training and validation loss while keeping the activated parameters constant.
So it makes the model far more compute efficient.
Exactly. More efficient learning. They also made a very deliberate trade-off with attention heads. while doubling attention heads from 64 to 128, like in DeepSeek v3, offered a modest, maybe 0.5% to 1.2% validation loss improvement.
Which sounds good on paper.
Right, but it caused a massive 83% increase in inference FLOPs for long contexts, like 128K sequence length.
Ouch. And agentic tasks often need that long context.
They absolutely require efficient long context processing for things like recalling past actions or understanding large code bases, so they smartly prioritized efficiency over those marginal performance gains. It's a very practical, engineering-driven decision.
That's a crucial distinction. Building something this large, especially within MoE architecture, usually introduces significant instability during training. I mean, loss spikes are almost expected.
They are, yeah.
What kind of challenges did Kimi K2's team face with that? And how did they manage to achieve such remarkable zero-loss spike stability over 15.5 trillion tokens? That sounds almost impossible.
It's a huge achievement, and that's precisely where their MuonClip optimizer comes in. It's really quite ingenious. They found their token-efficient Muon optimizer, while great for data processing speed, was prone to training instability due to something called exploding attention logits.
Exploding logits. Sounds dramatic.
It is. Think of it like a calculation inside the model suddenly spiraling out of control. Existing methods just weren't robust enough to handle it at this scale.
So what does KK-Clip do differently?
So they developed QK-Clip, a novel weight clipping mechanism. You can imagine it like a smart, targeted circuit breaker. It specifically rescales query and key projection weights after each update,
Okay.
but only applies per head clipping when a certain maximum logit threshold, which they set at 100, is exceeded.
So it's minimally invasive.
Oh,
Only acts when necessary.
exactly. This approach effectively tamed that instability, ensuring smooth, robust training across that massive 15.5 trillion token dataset. It's a genuine breakthrough in stability for these large-scale MoE models.
That's a really clever solution to a fundamental problem. Beyond the optimizer, you mentioned token efficiency being critical when high-quality human data is finite. How did they maximize the utility of their pre-training data? Did they just find more data, or was there something more strategic?
Oh, it was definitely more strategic than just finding more data, instead of just repeating data, which can lead to overfitting and diminishing returns anyway.
Right.
They introduced a rephrasing pipeline to generate high-quality synthetic data.
Okay, creating new data from old, how?
For knowledge-intensive text, they didn't just paraphrase simply. They used diverse prompting techniques to generate different styles and perspectives. And they combined this with a clever chunk-wise, autoregressive generation method to maintain global coherence even in very long documents.
So the generated text still made sense as a whole.
Exactly. They even showed concrete improvements, with rephrasing boosting simple QA accuracy quite significantly in some tests. And for mathematics data, they took high-quality documents and rewrote them into a learning note style, and even translated excellent materials from other languages.
Interesting.
This whole strategy is really about squeezing more intelligence and diversity out of every single token, essentially making their existing data go further and teach the model more effectively. And underpinning all of this, you have to remember their exceptionally robust training infrastructure. Kimi K2 was trained on NVIDIA H800 GPUs.
State-of-the-art hardware.
Yes, but used very smartly. They combined 16-way pipeline parallelism, 16-way expert parallelism, and 0-1 data parallelism. It's a complex setup. This wasn't just about throwing powerful hardware at the problem. It's about pioneering a blueprint for efficient, stable training of these trillion-parameter models, really pushing the boundaries of what's feasible in open-source AI development.
And they use specific techniques, too.
Oh yes, things like selective recomputation, using FP8 storage for less sensitive activations to save memory, and activation CPU offload to manage memory on each GPU, especially tricky with those complex MoE activations. The entire training process involved those 15.5 trillion tokens, with the context window extending all the way out to 128K using the yarn method, which is known for efficiently handling very long sequences without incurring massive computational cost.
Okay, so once this incredibly stable and efficient base model was built, the next massive challenge was teaching it the nuanced behaviors needed for true agentic intelligence. Things like tool use, complex problem solving. How did they bridge that gap from a powerful language model to an intelligent agent?
Right, this is where their post-training phase really stands out and gets quite innovative. They began with supervised fine-tuning, or SFT, using a massive instruction tuning dataset. That's pretty standard practice.
They probably put their own spin on it.
They emphasize prompt diversity and response quality, yes. But the truly innovative part, the real leap towards agentic ability, is their large-scale agentic data synthesis pipeline, specifically designed for teaching tool use learning.
Agentic data synthesis.
Okay.
Look at that ball.
Well, instead of relying solely on costly, slow, real-world interactions or limited human demonstrations.
Which is hard to scale.
Exactly. They developed a sophisticated simulation environment. Think of it like building a miniature AI universe specifically for training.
The universe for AI school.
Kind of, yeah. This pipeline has 3 clever stages. First, generating a huge repository of tool specifications. We're talking over 20,000 synthetic tools. They even visualize these using TSNE embeddings to show the diversity of tools created.
20,000 tools. Wow.
Yeah. Second, generating thousands of diverse agents and tasks, each with explicit rubrics defining what success looks like for that task. And finally, the crucial part, generating multi-turn trajectories where LLM-simulated users interact with these agents using the tools within a sophisticated tool simulator that provides realistic feedback, errors, and all.
So simulated practice sessions.
Exactly. But to ensure real-world authenticity, they didn't just rely on simulation. They complemented this with actual execution sandboxes, especially for coding and software engineering tasks, running these on Kubernetes for scalability.
That seems crucial for coding.
Absolutely. It's a brilliant way to generate diverse, high-quality tool use demonstrations at an unprecedented scale, far beyond what you could collect manually.
So they essentially built this miniature AI universe, complete with simulated users and tools.
That sounds
It's like a monumental undertaking. Was there a eureka moment in designing that simulation environment, or was it more of a grueling iterative process?
Well, the report suggests it was a highly iterative process, constantly refining the simulation's fidelity, making the feedback realistic, increasing the diversity of the generated data. It sounds like a lot of careful engineering.
Makes sense. And they also didn't stop at just fine-tuning with the synthetic data, right? They used reinforcement learning, RL.
Correct. They leveraged RL, which is often considered more token efficient for learning complex behaviors and can potentially generalize better than just supervised learning.
But RL for agentic tasks, especially involving tool use and planning. And I saw something about the model critiquing itself. That sounds like a whole different ballgame. What was the biggest hurdle there?
It is complex. Adapting RL effectively was key. For objective tasks like math, STEM, and logical reasoning, where there's a clear right or wrong answer, they developed verifiable rewards.
Okay, so rewards based on correctness.
Essentially, yes. They carefully selected problems of moderate difficulty, not too easy, not impossibly hard, to ensure strong, useful learning signals. For more complex instruction following, they used a hybrid verification framework. This combined code interpreters to check if code runs correctly, with an LLM as judge for assessing quality, and even added a hack check layer to detect if the model was trying to game the system or make deceptive claims.
A hack check layer. Interesting.
Yeah, and they also used a separate sentence-level faithfulness judge model as part of the reward signal to specifically boost overall factuality and reduce hallucination.
But what about subjective things? Like, is the answer helpful? Is it creative? You can't just verify those easily.
Exactly, and that's where the real innovation for these open-ended domains came in, the self-critique rubric reward mechanism.
Self-critique. So the model judges itself. How does that work?
It means the Kimi K2 critic model evaluates its own outputs. It does this by performing pairwise comparisons against a set of defined rubrics. These rubrics include core values like helpfulness and harmlessness, prescriptive rules to prevent what's known as reward hacking, where the model finds unintended loopholes to maximize reward without actually being good.
Gaming the system.
Right, and also human annotated rubrics reflecting nuanced preferences. This closed-loop process is fascinating because it allows the critic itself to refine its evaluation standards as the main policy model evolves. It extends alignment into these really tricky open-ended domains.
So the judge gets better as the main model gets better.
Precisely. It's like having a dedicated internal editor that's constantly learning and improving alongside the writer. They also refined the core RL algorithm with some crucial additions. Budget control was one.
What's that for?
To prevent the model from generating excessively long, rambling responses. It penalizes outputs that exceed task-specific token limits, keeps things concise and focused. They also added an auxiliary PTX loss. This helps prevent the model from forgetting valuable knowledge learned during pre-training while it's focusing on the new RL tasks.
Catastrophic forgetting, yeah.
Exactly. And finally, a temperature decay schedule. This allows the model to start with more exploration during RL, trying different things, and then gradually shift towards more stable, optimized exploitation of what it's learned.
That's a seriously complex interplay of algorithms, feedback loops, synthetic data. To run a system like this, especially with that self-critique loop constantly refining things, the underlying infrastructure itself must be a beast. How did they engineer the actual system to handle all these moving parts efficiently?
Efficiency was absolutely paramount. Their collocated architecture is a key element. This means having the training engines and the inference engines running on the same worker nodes in the cluster.
Why is that important?
It optimizes GPU resource usage significantly. You're not leaving GPUs idle while waiting for another part of the process. And for incredibly efficient engine switching, which is critical for rapid iteration in RL, where you're constantly updating the model based on new experience, they developed a distributed checkpoint engine. Get this. It can broadcast the full 1 trillion parameter model state across the entire cluster in less than 30 seconds.
30 seconds for a trillion parameters. That's incredibly fast.
It's lightning fast for a model of this scale, yes.
Nah.
Critical for making RL feasible. They also focus heavily on efficient system startup times and optimizing the agentic rollouts, the process of gathering experience. This involved handling those long-horizon, multi-turn tasks efficiently. They deployed heavy environments like complex simulators as dedicated services and used a technique called partial rollout.
Partial rollout.
It allows them to pause and resume long-running tasks without losing progress. Really important for complex, drawn-out, problem-solving scenarios where the agent might take many steps. It's really a holistic engineering masterpiece designed for this specific kind of large-scale agentic RL.
So we've explored the ingenious architecture, the incredibly robust pre-training with MuonClip, and this groundbreaking post-training pipeline for agentic capabilities. But okay, the proof is in the pudding. What does this all mean for real-world performance? How does Kimi K2 actually stack up against other cutting-edge models out there?
Well, the evaluations are incredibly compelling, especially when you remember this is an open-source model series. Kimi K2 Instruct demonstrates state-of-the-art performance among open-source models, particularly shining in agentic tasks and competitive coding.
Like software engineering.
Exactly. For example, it scored 65.8% on SWE Bench Verified and 53.7% on LiveCode Bench V6. These are challenging benchmarks, and those scores significantly close the gap with top proprietary models like, say, Claude 4 in those areas. For multi-turn tool use, which is core to agentic behavior, it sets a new open-source standard with 66.1% on Tautu Bench and 76.5% on ACES Bench.
So these aren't just abstract numbers. They really show a model that can genuinely act and solve problems in realistic software contexts.
That's the key takeaway, yes. It's showing practical capability. And in terms of general capabilities, Kimi K2 Instruct shows strong and importantly remarkably balanced performance across knowledge, math, instruction following, and long context tasks. It leads its open source peers on benchmarks like MMLU and MMLE Redux, achieving top-tier scores in math and STEM benchmarks as well.
And what about more subjective open-ended tests? How does it feel to interact with?
That's often the harder thing to measure, but what's particularly compelling for you, our listener, is its strong performance in those open-ended evaluations. It was ranked as the top 1 open source model and 5th overall on the highly competitive LMSYS Arena Leaderboard as of July 17, 2025. That's based on over 3,000 blind pairwise comparisons voted on by users.
So real people preferred it over many other models?
In many cases, yes. It also demonstrated a 65.4% win rate against ChatGPT-4, latest on a specific Chinese in-house benchmark, which showcases very strong multilingual capabilities in real-world scenarios too. And it's worth noting, even the pre-trained Kimi K2 base model before all the advanced agentic fine-tuning shows state-of-the-art performance for its size across most English language understanding and coding benchmarks and exceptional mathematical reasoning. It's a very strong foundation.
That's a truly impressive suite of results across the board. But of course, even with such strong performance, every model has its nuances, its quirks, and its limitations. What did the Kimi team find in their safety evaluations and internal tests? What should an ML engineer keep in mind if they were looking to potentially deploy this model?
Right, and they were quite transparent about this. Their safety evaluation was pretty thorough. It involved extensive red teaming, pitting Kimi K2 against other open source LLMs across various attack scenarios, harmful content generation, privacy issues, security vulnerabilities, using common strategies like prompt injection and iterative jailbreaking.
Out of it fair.
Kimi K2 showed relatively higher passing rates compared to some others in certain complex, harmful cases, which suggests good baseline robustness. Interestingly, they noted that simple obfuscation like base64 encoding had minimal impact on its robustness, but more sophisticated adversarial strategies like crescendo often led to a general drop in passing rates across models, including Kimi K2. It highlights that adversarial attacks are still a challenge.
And safety evaluation is tricky anyway.
Very much so. They openly acknowledge the inherent subjectivity in human review for safety evaluations and also point out that some tests, especially around harmful actions, are less relevant for base LLMs that don't have built-in tool calling capabilities activated. They also transparently listed some current limitations, which is really crucial for anyone thinking about practical deployment.
What sort of things?
For example, on very hard reasoning tasks, or sometimes when tool definitions provided to the model are unclear, the model might occasionally generate excessive tokens, basically, talk too much, leading to truncated outputs or incomplete tool calls.
Okay, so prompt engineering still matters.
Very much. Performance can also decline if tool use is unnecessarily enabled for a task where it's not needed, so context and how you frame the task is key. And importantly, for building complete, complex software projects, relying solely on one-shot prompting with Kimi K2 isn't going to be as effective as integrating it within a dedicated agentic coding framework that can manage the process over multiple steps.
Good to know. These sound like areas they've clearly identified for future improvement.
Exactly. It offers a clear roadmap for their own future research and development and for the community building on their work.
We've truly taken a deep dive today into Kimi K2. What we've seen is, well, it's not just another large language model, it's a strategically built foundation for agentic intelligence. They've pushed the boundaries in pre-training stability with that brilliant MuonClip optimizer and really revolutionized post-training with innovative agentic data synthesis and a sophisticated reinforcement learning framework that even includes self-critique.
Yeah, that combination is really powerful.
And its performance across agentic tasks, coding, math, and those open-ended scenarios positions it as a leading open-source LLM. It's a true testament to their engineering and research prowess. So you've heard about Kimi K2's impressive capabilities in allowing AI to autonomously learn and act. But maybe take a step back and think, what does it truly mean for your work, your research, or even just your basic understanding of AI when these models can move beyond static data and continuously evolve through direct interaction with dynamic environments? Consider the profound new challenges and opportunities this opens up, not just for human-AI collaboration, which will undoubtedly change, but perhaps for the very nature of intelligence itself. What does it mean when non-biological systems can learn and act this way? The Kimi K2 team has generously open-sourced their base and post-trained model checkpoints, so you can actually explore this groundbreaking work firsthand. Download them, experiment. Definitely keep a close eye on how agentic intelligence continues to evolve, because this deep dive, well, it's truly just the beginning of that story.